So ये वाली path, more delocalized electrons. So compared to calcium, they're going to have more delocalized electrons, and they're going to have a higher charge as well. Compared to Ca, transition metals will have a higher charge. So they will have a higher charge, and they'll also have more delocalized electrons. Now the question is how is that possible? So the answer to that is that like if you look at the electronic configuration of calcium, it's 20 electrons. That means the electronic configuration is going to be 1s2, 2s2, and it's going to be 2p6, 3s2, and then there is 3p6, then 4s2, and the 3d for calcium is empty. Like there's going to be 0 electrons in the 3d. So in the case of calcium, what happens is that there's a large gap that exists. Calcium can lose the outer 2 electrons, the 4s, it will form +2. But the next electrons, they're like very close to the nucleus. They're like really inside. So it's very hard to actually remove those electrons. So calcium can normally form a +2 ion. It can only have 2 electrons lost. Removing the other electrons is kind of difficult. So only 2 electrons are delocalized. Because removing the other electrons, you have to go really close to the nucleus. So the attraction for these electrons would be a lot more. But the same thing, if I write the electronic configuration of iron, for example, 26 protons. Now iron, Fe has 26 protons. And that's 1s2, 2s2, 2p, and 3s2 and 3p6, and there is 4s2 and 3d6. Now what happens is that the 3d and the 4s subshell have very similar energy levels. So one of the reasons why iron has variable oxidation states as well is that you can remove electrons from the outer 4s, but the difference between energy levels in the 3d and 4s, they're like really close together. So you can also remove electrons from the 3d as well. So that's one of the reasons why iron has variable oxidation states as well, that you can remove 2 electrons from the outermost, so that's 2 plus. But at the same time, you can also remove 3 electrons, or you can even remove 4 or 5 electrons, because you can remove electrons from the 3D, which is right next to it. So that's why iron can have more delocalized electrons. So यहाँ पे ना this thing. So the outer 4s electrons are delocalized. So outer 4s electrons are delocalized, but electrons can also be removed from the inner 3D subshell as well. And if they can be removed from the inner 3D subshell, what will happen is that more than, so you'll have variable oxidation state. And what's the reason why they can be removed? Because the 4s and the 3D have almost the same energy level. They have very similar energy levels. And you can have a look at the diagram as well for subshell energy levels. Do you guys think this one would be good enough? So I'll just copy the image and I'll put it there. जगह कम होगी एक से. You can have a look over here as well that the 4s and 3D have kind of like, they're really on the outside. I mean, the other orbitals, the subshells are like very close to the nucleus. The 1s is like really close to the nucleus, very hard to remove electrons. 2s, 2p, 3s, 3p. The 4s and 3d are like really on the outside and they're like really close together. So you can remove electrons from the 4s and you can also remove electrons from the 3d as well. So in the case of transition metals, unlike calcium, you have more options to have delocalized electrons. You can lose a lot more electrons. Is that clear? You clear, Sarasara? Is this clear? Abia, Hasib, Shian, is this clear?
Yes, sir.
So that's one thing that when you have a transition metal, right? So coming back to the point, इसको थोड़ा सा arrange कर ले. अच्छा, coming back to the point, let me just. That's this thing. That's why they have variable oxidation states. That is one of the reasons why they have variable oxidation states, because an atom, like if a chlorine atom comes in, it can lose electrons from the 4s. It can also lose electrons from 3d. So it can lose multiple electrons. So which is why iron can lose 2 electrons, and iron. But if you look at oxidation states of iron, iron's got lots of oxidation states. So, I mean, +2 and +3 are the common ones, the ones that you have mostly seen, but it goes up all the way up till +6. It depends on the other element, like how powerful an oxidizing agent is the other element. Like, so how many electrons it loses, it kind of depends on the other element. Like how many electrons can the other element take away from iron? So iron is definitely going to lose the 2 electrons. It will definitely form 2+, but it can also form 3+. It can electrons can be lost from the 3d, and you've got 6 electrons there. So more electrons can also be lost. So that's why they have variable oxidation states as well. So we can write about variable oxidation states over here as well. So we'll cover that as well. Just one second. Well, KC group, and I'll just add K. Hence, they have variable. So hence they have variable oxidation states. So they've got variable oxidation. States. So let me just explain this again. So a few things about so a few things about calcium and iron. So calcium, remember, can only lose 2 electrons, but iron over here, like if you think this is iron, so iron over here can lose a lot more than 2 electrons, because it's got a 3D subshell as well. That's so you can remove a lot of electrons from the 3D subshell as well. So the number of delocalized electrons would be a lot more. Plus, calcium can only form a +2 oxidation state, because it doesn't have a low lying 3D subshell. Iron can lose a lot more electrons. It's going to have a much more higher positive charge that can go up till +4. It can also go up till +6 as well. Definitely more than +2. Okay, so which is why, based on these 2-3 reasons, one is that the ion size is going to be smaller. You've got a smaller ionic radius, so the charge density will be higher. You're going to have a higher charge as well. Since you've got a higher charge and you've got more delocalized electrons as well. So at the end of the day, the ionic lattice is going to be a lot more stronger. Is that clear? The reasons are clear? Yes or no? Is this clear? So, so moving on. There's another point about high density as well. You remember we kind of summed up or covered 3 of the points. We're already done with 3 of them. Except for the high density part. Why do they have high density as well? So one thing is that by just looking at it, it obviously has high density because it's got a smaller size, so you can fit more of them, right? Plus, they're going to have a higher mass as well. Calcium has a mass of 40. Iron over here has a mass of 55.8. So one thing is that every single iron over here has a bigger mass compared to calcium. It's heavier. It's got more protons. It's got more neutrons. You move to the right. So when you move to the right, the atomic mass keeps on constantly increasing. So that's one thing. So density part is easy. And let me add that. Okay. So we can talk about higher density and sum this up. So higher density is they've got bigger atomic masses. Like copper is 63.5, calcium is just 40. So if they've got bigger atomic masses, which basically means that you've got more protons and neutrons compared to calcium. So compared, all of this is being compared to calcium. Secondly, you've got a smaller ionic radius as well. Because you've got more protons, you have the same number of shells, so the electrons are closer together, so smaller ionic radius. So more ions can be packed together. Hence, the end result is that you've got a huge difference in density. So more ions can be packed together, so that's why they're going to have higher density as well. ठीक है, is this all clear? ठीक है, सारा clear है? इसमें थोड़ा सा वो
Yes, sir.
अच्छा, और ये कि let me just highlight this. You get 2 reasons: delocalized electrons, and the other one is you've got more positive charge on the metal line. That pretty much sums it up. So we're kind of done with everything apart from colored complexes and good catalysts, right? So we're now going to move towards that thing. Okay, we've covered everything except for that. Now that's got nothing to do with. Actually, there's another thing that's related to this, and that's going to be catalyst. So we should cover catalysts before going to correct compounds. Now, what happens to catalysts? Like, why are they good catalysts? So good catalysts, and there are a number of cases. I mean, they're really good catalysts. So you've got iron in the Haber process. So you've got uh, vanadium V2O5 in the contact process. अच्छा फिर ये कि you've got okay nickel in the hydrogenation of margarine. Of alkenes or margarine or unsaturated vegetable oil. ठीक है, so a number of places where they're good catalysts. So what is a catalyst, by the way? Catalyst is that it reduces activation energy. So reduces activation energy, and less energy therefore is required to start the reaction. And so you get a faster reaction. Plus they remain.
अस्सलाम वालेकुम सर।
Islam.
सर आज थोड़ा सा कनेक्शन इशू था हमारे लाइक एरिया में, सिग्नल्स का इशू था, तो सर आप बता सकते हैं आज कितना हुआ?
वो तो मैं कर लेता हूँ, अभी कैटलेस से शुरू कर दो, ठीक है? ये कैटलेस हम कर रहे हैं तो अभी अपने स्टार्ट ही किया है कैटलेस, वो मैं फिर बाकी बता दूंगा। चलो ये वाला catalyst, you've got catalyst, they reduce activation, you've got a faster reaction, and they remain unchanged during the reaction, right? So when you talk about a catalyst, they might link it up with the Boltzmann distribution. Okay, what happens in the Boltzmann distribution is molecular energies are distributed in this way. Okay, molecular energies are distributed in this way. So this is the axis where you have all the energy, and this is the place where you have the number of energy is over here, the number of particles on the other side, or the percentage of particles. Okay. So you got the number of particles on this side, or the proportion of particles. Now, most of the particles, the height represents the number of particles at a specific energy. So most of the particles will have energy that would be around the average energy. That's the middle part, and that's your average energy. So then you're going to have particles at higher energy, but there will be very few of them. You'll have particles at lower energy, but there will be very few of them. So the height of the graph will be lesser. Okay, so fewer particles at higher energy, fewer particles at lower energy. Most particles would be, the maximum number of particles that you're going to have would be around the average energy. So they link this with catalyst as well. So what happens is that there's a point called activation energy. and that's your EA. That's the minimum energy that is needed to start a reaction. So minimum energy as a minimum energy needed to start a reaction. Any particle that has energy greater than the activation energy, that's the one, those are the particles that will successfully collide and react. Okay, so it's these particles that are going to have successful collisions. The other ones are not going to have successful collisions. Okay, because they don't really have sufficient energy to do that. So the other ones are not going to I mean, they're going to collide, but they're not going to successfully react. So what does a catalyst do? The catalyst makes it easier for the reaction to happen. So it reduces the activation energy. It reduces the amount of energy that is needed to start a reaction. So this is what a catalyst will do, that it will reduce the activation energy point. So आपकी जो नई activation energy होगी, so your activation energy in the catalyzed case will be this one. This is your EA when you add a catalyst. So now you've got more particles that have energy that is greater than activation energy. Okay? So remember, this axis over here is energy. And you've got more particles now, EV included. So all of these particles have energy that is greater than activation energy because the activation energy has decreased. So you get more successful collisions. क्योंकि ये particles भी बीच में add हो गए. More particles can successfully react. Okay, but anyways, they sometimes link a catalyst with Boltzmann distribution. Okay, I just wanted to go over this. Ye clear, Asana? Sidra, is this clear? Isha, Anna?
Yes, sir.
Achha, now this is AST. Okay, now coming back to the main point, which is what does a catalyst really do? So I'm going to start off with the Haber process. Why is it so hard for nitrogen and hydrogen to react? What's the reason for that? Why do they have such a high activation energy? So the thing is, now for every reaction, there's a different reason for why the reaction is not happening. So
triple bond of nitrogen.
So there's a triple bond of N, and there's an H2 molecule. So let's say you've got lots of H2 molecules, and you've got N2 molecules. Now, what should happen is that the bond should break. How do you break a bond? Like, why do you, agar wood ko burn karna, why do you have to give it energy? The reason you give it energy is that the molecules, they gain kinetic energy and they start flying around at a much higher speed. So this H2 molecule will be traveling with a lot more speed when you जब आप उसको energy देते हो, ठीक है? So it travels at a much higher speed. This H2 molecule will also travel at a much higher speed, and they're going to bump into the N2 molecule. Okay, this H2 molecule over here will also do the same. It's going to travel at a much higher speed. If you increase the energy, this H2 molecule will also do that. The purpose is, okay, when there's a collision, the old bonds, they get broken and then new bonds can be formed. Okay, so the whole purpose is of giving the molecules energy, and the reason why reaction happens when you give it energy is कि जो पुराने bonds and they all kind of break. If they don't break, then the reaction will not happen. So if you want to break the bonds, you would have to like make them really energetic. You would have to give them a lot of kinetic energy. So every reaction needs this minimum amount of energy that should be needed to break the bonds. तो आपके bonds टूटते हैं, that's the first step. ठीक है? So old bonds they get broken. And when old bonds are broken, that was the difficult part. So you're left with N atoms, you're left with H atoms. During the collision, the molecules they split up. And now, obviously, what can happen is that that new bonds can be formed. So once these bonds are broken, the next step is that new bonds are going to be formed, and that is bond formation. That's your easy part. You get the first part is the difficult part. So उसके बाद आराम से ना they'll just end up forming two molecules of NH3. You'll have one molecule of NH3 and then you'll have another molecule of NH3. Okay, so you'll end up with two molecules of NH3. So now old bonds getting broken, that's the difficult part. And what's difficult is that the triple bond is it's really strong. It requires a lot of energy. So difficult to break this N triple bond N. Large amounts of energy is needed for that. Because you need lots of energy needed. Hence they've got very high. Hence they've got very high activation energy. So difficult to break the N-triple bond. Okay, that's the reason. So how does adding an iron catalyst would actually make it easier to break this bond? Okay, this bond is like really difficult to break. So what happens is that when you add iron, transition metals have this very specific property, and that is they don't like to lose electrons. Transition metals are kind of unreactive. Okay, so let me discuss transition metals quickly. That why are they such good catalysts? Okay, so transition metals, due to higher proton numbers, so due to higher number of protons, what happens is that they actually lose their tendency to lose electrons. So they have a very weak tendency to actually lose electrons. For example, gold does not like to form ions. It doesn't like to lose electrons. Most transition metals are kind of unreactive. They don't like to. Copper does not. I mean, if you have a copper wire, it doesn't really react with a lot of things. So transition metals are due to. So transition metals due to higher number of protons have a very weak tendency to lose electrons. Again, this is what happens when you've got an element on the right side. You've got metals on the left side. Why do metals lose electrons? And they always like to lose electrons. They form positive ions, right? And you've got non-metals on the other side. They like to gain electrons. Why do they like to gain electrons? Because they've got a very strong tendency to attract electrons. What's the reason for that? They've got more protons. Okay? So the ones on the left side, they've got fewer protons in the nucleus, and over here you've got a large number of protons. On the right side. Okay, one example is calcium is over here. It's got 20 protons. Calcium likes to lose electrons, or even potassium. Let's make it potassium. Potassium is like really reactive. It's got 19 protons in its nucleus. In the same period, you've got bromine on the other side. Bromine on the other side has 35 protons. So obviously the one that's on the right side, it's got a very strong tendency to actually gain electrons. Now the transition metal is somewhere kind of in the middle between a metal and a non-metal. That's where, I mean, although call them a transition metal, but they're kind of in the middle. They're right in the middle. Okay, that's why they use the word transition, because you're kind of transitioning from a metal to a non-metal. And what happens with transition metal is, like, look at iron over here. Iron has 26 protons. So it's kind of in the middle. Like, you had potassium 19 protons. It doesn't really attract electrons. It loses electrons very easily. You've got bromine on the other side. It very strongly gains electrons. And you've got iron somewhere in the middle. So transition metals, they kind of lose their tendency to actually lose electrons. And they develop this very weak attraction for electrons. So instead, they slightly like to attract electrons. So is this idea clear, that you've got metals and you've got non-metals, and then you have transition metals right in the middle? The idea clear? So Siddha, is this clear? Partner, is one clear?
So,
Haji.
so they're kind of non-metals?
They're kind of in between. Okay, I mean, they don't like to lose electrons. They don't even like to gain electrons. They're like right in the middle. So platinum, and platinum is very unreactive, right? Platinum doesn't like to form ions. It doesn't like to lose electrons. Why doesn't it like to lose electrons? Because it strongly attracts its electrons. Okay? Even iron is very unreactive. Iron metal obviously used because it's very unreactive. It doesn't like to lose electrons. It doesn't like to get oxidized. It doesn't like to form ions. Okay? So copper doesn't like to form ions. So they don't like to lose electrons. Instead, they actually have this slight tendency to attract electrons. So they develop this very, very slight tendency to attract electrons. But it's very slight. It's not like a non-metal. You get non-metal to ulta electron को gain कर लेता है ना. जिसका अगर bromine होगा, it has a very powerful tendency to actually attract electrons. It's going to gain that electron. It's going to become -1. Iron ये काम नहीं करेगा. Iron is not going to gain electrons, but it has this attraction for electrons. ठीक है? तो वो कहीं middle में है. Now, why is that important? Why is that important in context of the Haber process? The reason that's important is, okay, this iron will do two things. It will make it easier to break the N triple bond N. तो यहाँ पे ना अगर आपके पास इसको बस खत्म कर लेते हैं ये. Here's your iron. If the N triple bond N molecule comes very close to it, and the H2 molecule comes very close to it, H2 का bond तोड़ना तो वैसे ही it wasn't that big an issue, right? So you got this. I say we've got these molecules coming in, and they're striking the iron catalyst. What will happen is, okay, iron will start to attract electrons. It's going to start to attract electrons from the bonds. You can remember it's got this very, very weak attraction for electrons, like a non-metal, but not a very strong attraction. So it's not going to keep those electrons, but it will weakly attract those electrons. Okay? So when these molecules, they come in, they come very close to the iron. So the bonded electrons, that were once part of the bond, these electrons, they eventually get attracted to the iron, and they get absorbed by the iron. They form weak bonds with iron. ठीक है, these are very weak attractive forces, not that strong, ठीक है, क्योंकि अगर वो strongly attract करता ना, the N2 would never be able to leave. So it's a very weak bond, it's a very weak attractive forces. But what this weak attractive force has done is it has broken the triple bond. ठीक है, previously it was very hard to actually break the triple bond, लेकिन यहाँ से ना iron started attracting the electrons that were part of the triple bond. So the electrons in the middle center, they got dragged and they got closer to iron. And in the next step, there's going to be deadsorption, which is that these molecules will, once adsorption has happened, these molecules have a certain amount of kinetic energy. So they're going to fly off. They're going to hit the catalyst, and they're going to bounce back. So all of these, after striking the catalyst, they would eventually bounce back. And when they do that, so remember the bonds were like very weak. So these weak bonds all of them are going to break. But during the process, what has actually taken place is that
Sir, is this an example of heterogeneous catalysis?
This is an example of heterogeneous catalysis, yes. Okay, and this is, so let me just write this. This is deadsorption happening. Okay, deadsorption is that the weak bonds, because iron was never going to gain those electrons. Iron didn't have a strong tendency to attract electrons, it just had a weak tendency to attract electrons. So the weak bonds would eventually break. So deadsorption is that the weak bonds between catalyst and the first part is adsorption. Adsorption is that, so adsorption is the catalyst weakly bonds to reactant molecules. It weakly bonds to reactant molecules, weakening the older bonds. So it weakens the older bonds. So that's adsorption and deadsorption, and this is an example of a, so this one over here is an example of heterogeneous catalyst. Okay, and what's a heterogeneous catalyst will be, it's what's a heterogeneous catalyst? That the reactant and catalyst will have a different state. So okay, next time continue karenge, we'll just talk about the other type of catalyst. Okay, I'll complete this, but just remember that why are they good catalysts? Because they're kind of in the middle. They don't like to lose electrons, they don't like to even gain electrons. So instead, so why would a non-metal be a very bad catalyst? Because what a non-metal would do is कि वो उसके electrons को gain ही कर लेगा, उसको छोड़ेगा ही नहीं, ठीक है? Non-metal will form a very strong bond. If it had been chlorine over here, तो वो nitrogen के electrons को pull करके अपने साथ ही रख लेता, ठीक है? It would not let go of those electrons. Iron will not do that. Iron will just very, very weakly attract those electrons. So ठीक है, let's continue this. Continue with this. हाँ जी.
सर सॉरी थोड़ा सा कनेक्शन का इशू था, ये आप जो एग्जांपल है फिर से एक्सप्लेन कर सकते हैं इसके अंदर?
नहीं, वीडियो लिंक इसका वो आ जाएगा ना, वीडियो वैसे में दूसरी क्लास शुरू हो रही है, कल मैं एक्सप्लेन कर दूंगा, ओवरव्यू दे दूंगा, ठीक है?
ओके।
अच्छा एक सेकंड, ये मैं बोर्ड लिंक उसी पे भेज रहा हूँ, ठीक है? व्हाट्सएप पे। ओके, टेक केयर, ऑफिस।